They both agree that back in 2003 and just 3 years ago, that the state of practice in terms of soil sampling has regressed over the years in spite of clear knowledge of best practice methods. And before to continue with this presentation, I need to mention that this presentation focuses mainly on soft to medium soil that can be sampled with standard pushed samplers. So they have recognized that the reason why we have regressed in best practice methods over the past years and decades is basically due to two main factors. The first one is the poor sampling methods we normally adopted in practice. And the second one is a consequence of the first one, which is a poor selection of soil parameters. If we just focus on the sampling techniques that we have available, we have two main different trends. We can have block sampling if the conditions of the ground allow us to do that, and also the sampling depth is not really deep. And on the right-hand side, you see the tube sampling techniques. Within the tube sampling techniques, we have two main samplers available. The Shelby tubes or the open samplers, and then fixed piston samplers. The first conclusion is, and I will try my best to highlight the fact that Shelby tubes are not by any means a good option for sampling soft soils. I strongly not recommend the use of Shelby tubes, and I know that sometimes these sound a little bit too strong for in practice, but I will try to give proper scientific justification for that statement. So what happens with the open samplers with the Shelby tubes is that we have here on the left hand side the sketch how this the operational principle of that. We push the sampler into the natural ground, and there is nothing inside to prevent any entrance of mud or remolded soil into the sampler, and that's the main problem that this sampler has. And then we have some vents for all the water inside or the mud to basically flow out. But as I have discussed before, if you check this CT scan for another Shelby sample we have tested in our lab, you see that there are in almost 99% of the cases that we have seen in our lab, Shelby tubes are really bad quality when you scan them, when you see through them, and you see vertical cracks, subhorizontal cracks, also fissures and cavities. And the problem with these is that the Shelby tubes are the most common sampler used in Australia, and we have been trying over the past decade and a little bit more to push for a change, talking to practitioners like you guys and talking to RMS, now Transport for New South Wales, in order to modify the guidelines and recommend something else. On the bottom left-hand side, you see a photograph of the mini Sherbrooke block sampler. This is a reduced version of the original Sherbrooke sampler developed in Canada in 1979. So the original Sherbrooke sampler required a 400 millimeter borehole in order to be used. The NGI from Norway, the Norwegian Geotechnical Institute, decided to redesign the sampler, and now this is the option. The option has the reduced version has a diameter of 180 millimeters. To use it, you have to have a 200 millimeter borehole. Then the height of the sample that you can get is up to 250 millimeter, from which you can get several triaxial and odometer samples for laboratory testing. The sampler itself is composed by a metallic cage that you can see here. They have annular slots or horizontal cutters on this side. I'm trying to indicate that with my cursor. And also at the base, we do have 3 bottom metallic blades, horizontal blades. These springs are going to activate the horizontal closing of these bottom blades. So those springs are going to nicely and gently start to move the blades from the outside of the sampler towards the center. And at the end of this operation, the base of the sample is going to be fully cutted, and these 3 blades will serve as a support for the block sample to be retrieved to the ground surface. After that, which in my opinion is one of the most complicated operations in this technique, is we need to retrieve the tube with the sample inside. And if we use Shelby tubes, what happens is that we create, when we try to pull the tube sampler from the ground, we create suction at the base of the tube, because we need to cut the base of the soil inside the tube, and we need to disconnect it from the natural ground. That pulling induces suction at this point at the base, which basically induces water redistribution inside the soil. Therefore, we are changing the natural water content in the soil and therefore the density in our specimen. And we don't know by how much this suction is affecting our soil quality. After that, we got the sample in the ground and we need to seal it to minimize moisture losses. And we normally use melted wax. To protect the sample, we put melted wax on the top and bottom ends, as you can see in this sketch at the bottom left-hand side. But wax must be liquid or semi-liquid, and that means that the wax induces a thermal gradient that travels from the tube two ends towards the center of the sample, inducing most likely an excess pore water pressure in the case that there is no volume change. In the case that we do have volume change inside the soil, because you have cracks, you have cavities, then we have also soil deformation here, and this changes the density of the natural soil that we want to test further, and from which we want to obtain soil parameters for geotechnical design. Transport and sample storage. We normally promote the option of keeping the tubes vertically aligned, not horizontally aligned, in order to avoid the natural soil inside the tube to flow. And we have seen quite a few examples of tube specimens that are transported and then shipped to the lab in a horizontal position. And then when you try to open them up, basically they flow like a toothpaste, because there are some cavities and the soil is allowed to move inside, and that's not good. This also induces some negative changes in the natural structure of the soil. And this is potentially one of the key messages of my talk today. So there are two main trends. So we have non-destructive techniques, which are good because we want to check if the sample, our quality is good enough before doing any test. And I'm going to highlight only one, which is the image technique that qualitative and quantitative analysis we have developed at the University of Newcastle based on CT scans. But the more standard procedure is based on mechanical tests. So these tables at the base basically summarize the methods that you can have in practice. So we have used this index from NGI delta E by 0 for all these samples that we have tested. This is the pre-consolidation stress. According to this index, the only two samplers that provide us with good quality, excellent quality samples are the block sampler and the fixed piston. The free piston is more or less good in this case, and the Shelby tube give us very poor sample quality. The M modulus, the odometer modulus, the same thing. Only the block and the fixed piston gives us the high quality specimens, and the Shelby always gives us the very poor sample quality. In terms of the simple shear, more or less the same. So the Shelby tube gives us the poor sample quality. And if we estimate the strain at peak condition, you see that it's only required 2 or 3% for the block and the fixed piston to reach the peak value, whereas it requires a lot of deformation for the Shelby tube to reach the peak condition. So clearly, Shelby tubes are not good. The main problem with this method is you need to run the test, and at the end of the test, you realize if everything you have done is good or bad, which is definitely not good. So that's why we are proposing a different method. So this is a qualitative assessment of sample quality using CT scans. You see the two Shelby tubes. These are scans that I already showed to you both. You see all of these tubes has cracks and defects and cavities. In the middle, you see the free piston sampler. The free piston is better, but you see that there are still more subhorizontal cracking. The only one that has only cracking at top or fissuring top and bottom ends is the Shelby tube, and therefore, the Shelby tube, the fixed piston sampler. Sorry about that. So the fixed piston sampler gives you really good quality along the entire tube, except top and bottom ends, which is really good and good enough for practitioners to be using geotechnical design. So the way we have used it in a qualitative way is just sketched here. So we have the CT scan, and then we decide where we can trim samples for odometer test or CRS, and also triaxial test. And we can also detect that the presence of shells or cobbles or any other stone that you cannot test in the lab. So therefore, you decide for this tube only to run one triaxial and one CRS, and that's it. The other part of the tube cannot be used. So the final take-home message is basically sample disturbance must be recognized for a process that we have many factors that may induce may have negative impacts on sample quality and therefore in soil properties. Shelby tube should be avoided. I strongly recommend don't use them just in the standard version. So you can use it for as part of the fixed piston samples. Fixed piston samplers should be used, is by far much better than Shelby tubes. In cases where there is room and money to use the mini Sherbrooke, we are more than happy to collaborate with industry, providing our block sampler for this type of jobs. And finally, we are proposing a new method that hopefully could be adopted by many practitioners, and we can try to all of us move forward to a better practice in Australia.